So, the first thing you need to know about carbohydrates is the structure of glucose in its cyclic hemiacetal form. You may already know this because we talked about it before a lot in chapter 14 when we talked about acetals. So, you draw a chair, one oxygen in the ring, and then we're going to draw the form of glucose that looks like this. And this form of glucose is easy because everything is equatorial. And this molecule has a technical name. Glucose, or D-glucose, refers to the open chain form of the molecule. In this form, we call it beta-D-glucopyranose. All right, so that's kind of fun. So what do all of those names refer to? Let's start with the D. D refers to this stereocenter here. Now there's a hydrogen on that carbon that's sort of at a down position in the six-membered ring chair form. And the hydrogen's pointing downward. We're not drawing it, you have to imagine it, it's there. That is a stereocenter, and the configuration of this molecule, the D refers to the configuration of that stereocenter. It's kind of weird. It's an old-time tradition related to back when you couldn't really get the absolute configuration of a stereocenter, but you could get it sort of by analogy to other things. So there were two forms of, I believe glyceraldehyde was the molecule, and one was D and one was L. And then if your stereocenter had the same configuration as the stereocenter from D-glyceraldehyde, it was called D. So when we draw glucose this way, the D configuration has this CH2OH group, this hydroxymethyl group, pointing upward at an up equatorial position. All right, so that's D, that's the D in glucose. The beta is interesting. The beta refers to this stereocenter here. And when it's beta, the OH is on the same side of the ring as the hydroxymethyl group. Okay? So beta sort of refers to OH and the C1OH and the C5 CH2OH are cis to each other. Okay? Another way of thinking it is when you draw D-glucose in this configuration, beta means the OH on this carbon is up. All right? That carbon is interesting. We're going to talk about it a little bit later, but you will recognize it as the hemiacetal carbon. And so we have a word for that carbon, and it is the anomeric carbon. That's another way of saying the hemiacetal carbon. And we will sometimes call beta D, no, thank you, later. We will sometimes call beta D glucose the beta anomer, meaning it's got beta configuration at the anomeric carbon. That's the hemiacetal carbon. You can recognize it as such because it's got an OR group, this oxygen bonded to this carbon, and then an OH group on the same carbon. That's the hemiacetal carbon. Okay, what about gluco? What does that tell you? It turns out that gluco tells you the configuration of C2, C3, and C4. And so just to help us out, I'll number the atoms of the ring. 1, 2, or carbons anyway, 3, 4, and then 5. So beta refers to configuration at C1 as relating to C5. D refers to configuration at C5. And then gluco refers to configuration at C2, C3, and C4. And the best way to remember this is just when you draw glucose in its chair form, more stable chair form, C2, C3, and C4 OH groups are all equatorial. Up or down depending on which carbon that they're on, but they're all equatorial. You guys remember what equatorial versus axial is? You remember what up versus down is on a 6-membered ring? So you're okay that this is an equatorial OH group, but it's pointing down. This one's equatorial, that's pointing up. Okay, good. All right, and then OS here tells you that the molecule is a carbohydrate. So that is the sort of suffix that's appropriate for carbohydrates. And then pyran refers to, I don't know if we can tell the difference between purple and whatever on the screen. Close enough. Pyran refers to cyclic form. A pyran specifically is a 6-membered ring with 1 oxygen in the ring. So when you see beta-D-glucopyranose, that tells you that it's glucose in its cyclic hemiacetal form, and the anomeric carbon has the beta configuration and it's D-glucose. Right? Questions about that? Okay, let's show you the alpha version of D-glucopyranose. So the alpha version is going to have the exact same configuration at all of the rest of the stereocenters, but at C1, the OH group is going to be down instead of up. So this is alpha D-glucopyranose. And again, another way to tell that it's the alpha anomer is to pay attention to the configuration of the C5 stereocenter, which is going to be up when drawn this way. Alpha means you're opposite to that hydroxymethyl group on C5. So for the alpha anomer, it's the C1 hydroxy and the C5 hydroxymethyl group are trans to each other. Other than that, everything's the same. The relationship between the alpha and the beta anomers, well, you tell me, what is the stereochemical relationship between those two? What would you say? Enantiomers, diastereomers, some other kind of isomer? Yeah, diastereomers. Remembering that if 2 molecules are stereoisomers but they're not enantiomers, they have to be diastereomers. We've got another word that is related to diastereomers. I've already alluded to it. We can say that the alpha and the beta stereoisomers are anomers of each other. That simply means diastereomers that differ at the anomeric carbon. And another term that you will hear is epimers. Epimers means they differ at 1 stereocenter. So you will hear people use these terms to talk about the relationship between the alpha and the beta anomers. They are diastereomers. They differ at the configuration of the anomeric carbon. They're also epimers because they differ in stereochemistry at 1 and only 1 stereocenter. Okay. Other questions about the vocabulary? All right. Let's do a little bit with the open chain form, a little bit with interchange between the 2 anomers. So this is something that you will have seen before, and in fact you've answered questions before on an exam about this, where I've given you a cyclic carbohydrate and you've had to draw me the open chain form. And the big challenge there was actually not dealing with hydrolysis of the hemiacetal. The big challenge there was getting the stereochemistry right everywhere. So you probably want to review that again, because I can certainly imagine that kind of thing coming up. But let's show you a little bit about ring opening. I mean, I am evil, but like most villains, I give away a lot in my monologuing, so just pay attention and you know what to expect. So here's the beta anomer. All right, and then the ring open form. And in aqueous solution, generally the cyclic hemiacetal form is more stable. The ring open form is going to look like this. It's this aldehyde. And you can tell that the open chain form of beta-D glucopyranose is an aldehyde because if you look at the anomeric carbon, what it's got attached to it other than the oxygens is a carbon and a hydrogen. So in the open chain form, it's going to be an aldehyde. In the open chain form, it is simply called D-glucose. Now, there are a couple of ways you could think about opening up the ring. Let me show you how we did it in chapter 14. Remember that in order to open up the ring, this OH group has to end up as the carbonyl carbon. And so it's going to need to kick off the ether oxygen as a leaving group. The problem is that a neutral oxygen can't kick off a negatively charged oxygen. That's been an exam question before too, and may yet be again. So what you need to do first is protonate the oxygen. If you were in water, that would be H3O plus, and even a very small amount of H3O plus that's present at pH 7 would be enough. For the most part in the past, we've been sort of generic about that, so we would protonate the ring oxygen first. To get the following oxonium ion that's protonated on the ring oxygen, positive formal charge. Then it's a sufficiently good leaving group for a neutral OH to kick off that leaving group. That will lead to a second oxonium ion now that looks like an aldehyde, and this is ring opened, but the aldehyde is protonated on the carbonyl oxygen, and we would regenerate our base catalyst. We would regenerate our the acid using the conjugate base of our acid to remove that proton, and then that gets us to D-glucose. So that's ring opening. That mechanism is fine. And a colleague pointed out to me not long ago something that I don't know that I ever knew, and so it's kind of cool, so I thought I would show it to you. This is a valid mechanism for ring opening as well. So you simply and this mechanism sort of points out how ring opening can happen in water. No, I still want those labels there. Let's put, except here, I'm going to put the hydrogen here. Can you sort of see how with this oxygen, this carbon, this oxygen, and this hydrogen, we've sort of started to form the edge of another chair? If you put an oxygen from water here and a hydrogen from water here, you can see that the hydrogen from this water molecule, and I haven't completed it yet, so stay tuned, is very close to this oxygen. Gotta try again, didn't like that. There we go. So water can actually catalyze the ring opening in a single step, and the reason that's possible is because a single water molecule can be in the right place to act simultaneously as acid and base. So this is kind of cool. What will happen is Lone pairs on this water-oxygen will remove this proton. At the same time, these electrons will kick down to kick off the leaving group. I'm going to put that arrow on the other side like that to make the carbon-oxygen pi bond. And as the leaving group is leaving, it picks up a proton right away, so it never has to be negatively charged. So this sort of cyclic proton transfer type of mechanism is probably what actually happens when the molecule's opening up, because you don't need an acid to come by, then float away, then the base to come back in. The single molecule acts as both acid and base at the same time. I know there's a lot of arrows going on there. I know that maybe it would have been difficult to predict that. Go back and look at this mechanism and convince yourself that water is fulfilling this role here as proton donor and this role here as proton acceptor all at the same time. Okay. So that's ring opening. Let's talk about interchange between alpha and beta anomers, okay? Because one of the things I didn't tell you, even though these two are stereoisomers, they're in equilibrium with each other in solution. And how they interchange with each other is interesting and important. So one of the ways they can interchange with each other is simply via the open chain form D-glucose, right? Because you can see if we get to that open chain form of glucose, by rotation around the bond between C1 and C2, you can redraw the structure like this. And now the aldehyde carbonyl is pointing downward. Okay, and the proton is pointing upward. And then I won't draw the mechanism for this, or maybe I will. Should I? Why not? Water can probably do this as well, though the fact that it's sort of six-membered ring transition state is going to be difficult to see, because there is a chair going on here, but it's not easily visible. What will happen again is oxygen will act as a proton acceptor, stealing the proton from the C5 hydroxyl group. At the same time as that bond is breaking, the C5 hydroxyl will attack the carbonyl on C1. At the same time as that pi bond is breaking, water will protonate, act as a proton donor to protonate the carbonyl, and that will get us to the alpha anomer. So that's one way in which we can interchange alpha and beta anomers simply by ring opening, followed by rotation, followed by ring closing. And they call this process the interchange between alpha and beta anomers. They call that mutarotation. It's not really rotation in the sense that you can't get from the beta anomer to the alpha anomer by simply by rotation around a carbon-carbon bond. You have to open up the bond, open up the ring, and then rotate. But they call that process mutarotation, and the alpha and the beta anomers are in exchange with each other in aqueous solution. There's an alternative mechanism for mutarotation that probably happens too, and we need to talk about this because it's useful in other areas for carbohydrate chemistry. So this was an alternative mechanism for ring opening. By the way, up here, the ring closing mechanism I showed all in the same step with 1, 2, 3, 4, 5, 6 atoms. You could show that stepwise and that would be entirely fine. Needless to say, you're not going to face a test question where I show you this one and a equivalent stepwise one and ask you to choose which one I happen to be thinking about at the moment, right? They're both correct. An alternative mechanism for mutarotation, an alternative pathway is as follows. So you start with the beta anomer of glucose. You protonate the C1 hydroxyl, and the amount of hydronium that's present in aqueous solution at pH 7 would be sufficient for this. You protonate that C1 hydroxyl, turning it into a good leaving group. And then the neutral ring oxygen is a sufficiently good kicker-offer to kick off the water leaving group. And that will generate the following oxonium ion that looks like this. With a positive formal charge on the oxygen. That is a resonance stabilized cation. You could draw a resonance structure that would look like this with the positive formal charge on C1, which tells you that this molecule, because oxygen's more electronegative than carbon, you infer that this molecule is mostly electrophilic on C1. This ion, you could call it an oxonium ion because it has a positive formal charge on oxygen, though in this resonance structure we would call this an oxocarbenium ion. Carbenium is a term we use for carbocations. Both of these terms are interchangeable, and they refer, in the case of this cyclic molecule, to a resonance stabilized carbocation that has an adjacent lone pair on the oxygen. Okay? Then you can see how we get the alpha anomer if we have water attack the oxocarbenium ion from below instead of from above. If water attacked from above, we would simply go back to the beta anomer. If water attacks from below, then we make the new bond with oxygen in this equatorial position. And then at that point, getting to the alpha anomer is simply a matter of using the conjugate base of our acid to deprotonate the oxygen. And that's another way we can get to the alpha anomer. So two different mechanisms. I don't actually know which one is the most operative one in aqueous solution, but both are valid ways for interconverting the beta anomer and the alpha anomer. Right. And we will see when we do chemistry with carbohydrates, we'll see that often it's going to involve an oxocarbenium ion that's going to get attacked by something else. In this case, it was water, but you could ask the question, what if the nucleophile instead of water here was an alcohol? And then attack at the carbonyl carbon would give you not the anomer of glucose, but perhaps an acetal form. So we'll return to that idea in a second. Questions so far? Let's see, what is my computer trying to remind us? Delete, delete. Okay. Let's talk a little bit more about the alpha and the beta anomers. You now have the idea that they're in equilibrium with each other. And if they're in equilibrium with each other, the relative amount of each one should be more or less related to their relative stability. So there's the beta anomer. And here is the alpha anomer. And as I said, they're in equilibrium with each other. So, you learned some things in 351 that maybe should allow you to make a prediction about which anomer is more stable. So what do you think is going on? Which is better? You think beta is better because axial versus equatorial. So you guys learned back in 351, if I could just come over here to Spartan and make a space-filling model, you learned that it's better to have groups axial versus equatorial. Here's a cyclohexane ring with an equatorial methyl group, and we're going to show that space filling. You learned that it's better to have groups equatorial than axial. Now the methyl group is axial, and you can see that that methyl group is leaning away. It's not perfectly parallel to the other axial protons. It's leaning away because of sterics. And if I show you a space-filling model, you can see that the methyl group is bumping into the other axial hydrogens. So yeah, being in an axial position results in what we've called 1,3 diaxial interactions. They're sterically bumping into each other. That's electron-electron repulsive, and it's destabilizing. Now, you may have learned, I'm not sure if you learned this in 351, but in 351, or rather organic chemists have tabulated a thing called an A value, which tells you how much worse it is in free energy to have a group axial versus equatorial. And we use that sometimes as a measure for how big something is. For an OH group, the A value is 1 kilocalorie per mole. So, you could hypothesize that if sterics is the only factor here, the only thing that's making the alpha anomer different in energy than the beta anomer, you would expect the free energy of this reaction to be basically the A value, right? You would expect conversion from beta to alpha to be around 1 kilocalorie per mole. And you can turn free energies through, you don't want to do math and neither do I, somebody's done the math for us already, but through the relationship delta G equals RT ln K, you can turn this 1 kilocalorie per mole expected difference in free energy into a ratio of alpha and beta anomers. Okay, this is not Gen Chem, so we're not going to do that math. Put your calculators away. Yay, right? But you'll have to take it for granted that if sterics is the only factor and we expect delta G to be about 1 kilocalorie per mole, then we expect a ratio of beta to alpha anomers of about 75% to 25%. Okay? And somehow I can't spell ratio. There's an O at the end, not an N. I don't know. Instead, we observe a slight difference from that. It's actually, instead of being about 3 to 1, it's only 2 to 1. That should be like 33, sorry. This is why we don't do math in this class, because we can't do arithmetic very fast, or at least I can't. So yeah, instead of a 3-to-1 ratio, it's more like 2-to-1, which means that the alpha anomer is unexpectedly stable. It's not more stable than the beta anomer, but it's more stable than we would have expected based on sterics being the only factor. So we conclude something else. That's a symbol from math. The 3 dots mean therefore, okay? Sorry, I will do that. I learned that in junior high when we were doing geometry proofs. There was 3 little dots, therefore, at the end. Therefore, angle A is equal to angle B, or whatever. And that's a simpler way to write therefore, so just run with it. It's not Hobbit scripting. I think sometimes in Hobbit scripting you'd use the 3 dots for like eyes or just random flourishes, but no. Okay, sorry, weird aside. So therefore, something other than sterics must be working here and must explain the alpha anomer's unexpected stability. So a good rule of thumb in organic chemistry is if it's not sterics, it's likely to be electronics. If it doesn't have to do with sterics, it likely has to do with something that's going on with electron density and electron delocalization. So, and this isn't the most important topic, but it is an illustration of something that you've learned before, so we'll talk about it here. And my students in the past have joked, if you don't know the answer and you guess hyperconjugation, it's often correct. So recall that hyperconjugation means in the same molecule, overlap of a filled orbital with an adjacent empty orbital. And the filled orbital is usually, it can be a non-bonding lone pair, it can be a sigma bonding orbital, say a carbon-hydrogen sigma bonding orbital. The empty orbital could be a sigma star, it could be a pi star, it could be an empty p orbital. We've seen some of these things before. What's going on with the alpha anomer, if we zoom in, is that you have at C1, you have a carbon-oxygen sigma star antibonding orbital that's pointing, and here is the node to that antibonding orbital. A sigma star antibonding orbital looks like this. It has a node in between the 2 atoms, and then it has larger lobes outside of the space between the 2 atoms. And there's a switch in wave function sign at the individual atoms themselves. So there's a node here at the carbon, there's a node here between the carbon and the oxygen, and there's a node here at the oxygen. I've just labeled the one node that's in between the 2 bonds. This is an empty sigma star antibonding orbital. And it's adjacent to or lining up with a non-bonding lone pair on the adjacent oxygen. What kind of orbital is that in? It's likely in some kind of hybrid orbital, if you want to think of that as being sort of in an sp3 type hybridized orbital on oxygen, that would be okay. I'm drawing just one of the lobes of that sp3 orbital. There would be a smaller lobe here on the other side of the oxygen that I won't draw. And hyperconjugation means partial delocalization, not complete delocalization, but partial filling of this lone pair into that antibonding orbital. That allows the electrons to move lower in energy, and it pushes the antibonding orbital even higher in energy. It does lengthen the bond between carbon and oxygen a little bit, but not enough to break it. And so overall, it's stabilizing. That's possible in the alpha anomer because the axial down OH group puts the sigma star right and lined up with the adjacent lone pair. We won't draw this, but I'll just highlight it here. There's better what we would call N to sigma star hyperconjugation in the alpha anomer than in the beta anomer. The idea is if you go up and look at the beta anomer, the sigma star antibonding orbital would be projecting down here away from the lone pairs on the oxygen, not lining up with them, and therefore unable to interact or be stabilized. So it's thought that the reason the alpha anomer is more stable than expected is because of this hyperconjugation effect. And you can probably put a number on it, and it's probably, about 0.1, 0.2, 0.3 kcals per mole. That sounds small, though it's enough to move the needle in terms of equilibrium constant, which is why we're talking about it. The unexpected stability of the alpha anomer is called the anomeric effect, and organic chemists will use this sometimes in we'll use this in carbohydrate chemistry to help bias reactions from one direction to another. All right, questions about that? Yes?
I was trying to wrap my head around how the delocalization with an antibonding orbital makes it more stable. In my head, it's like, wouldn't that make it?
Right, and that's an important question that people often have. Why does delocalization into an antibonding make things more stable? So there is an answer to this, and it may be complicated enough that it's beyond the scope of the class. The way to think about it is electrons spreading out lowers their energy, lowers their kinetic energy, makes them lower in energy. So basically what hyperconjugation is you have a filled orbital here and an empty orbital, a sigma star up here. This is a non-bonding lone pair. And they will mix together to make a slightly lower in energy version of the lone pair and a slightly higher in energy version of the antibonding orbital. And the lone pair is lower in energy, which is great. The antibonding orbital is higher in energy, which doesn't matter because it's empty. So this may be the destabilization you're expecting. It doesn't matter because it's empty. Now you're right, I've taught you that if you fill an antibonding orbital completely, the bond breaks. And I think that's the sort of mix-up, and what I would say is that we're not filling it completely. Okay, what else? Okay, yeah, go ahead.
What does the N stand for?
N stands for non-bonding lone pair. Okay, what else? All right, so now we've talked about that. Let me introduce a couple other carbohydrates that you ought to be aware of. And these are structures that I want you to memorize. So obviously glucose, beta-D-glucopyranose or its alpha form are structures that is a structure you need to have memorized. What I'm going to talk about now are epimers of glucose. These are molecules that differ at C2, C3, or C4. Now, as you can imagine, you've drawn glucose so many times that you don't need to draw it again, but I want it for reference, so I'm just going to copy it. You can imagine that with all of those stereocenters, 1, 2, 3, 4, 5 stereocenters, there would be, let's see, 2 to the 5, which, why am I not doing that in my head? 16, 32, 64? Somebody else is doing the math. 32? Okay, I told you I can't do arithmetic fast. I also can't tell my right hand from my left hand on the first try. I mean, I can, but if you ask me to say, I will often say right. even though it's my left. I get it mixed up on the first try, sorry. Anyway, 32 different stereoisomers. And they all have names. We're only going to, 16 of them would be D, 16 of them would be L. We're only going to learn 3. Well, yeah, 3. We're going to learn, 6, because we're going to learn both alpha and beta forms. But that doesn't count, because you know what alpha and beta are, so that's easy. So this is beta D glucopyranose. The rest of the 3 other ones we're going to learn also are going to have the same rules for beta and D and pyranose, but we're going to change the part that talks about stereochemistry at C2, C3, and C4. So, for example, if we change stereochemistry at C2 to make the C2 epimer of glucose, we're going to draw exactly the same thing, keep everything else the same, only at C2, we're going to have an up axial OH group at C2. This is going to be called beta D manopyranose, and in its open chain form, we would call it D mannose. And this is a common carbohydrate found in biology. It's used for different things than glucose is. Your body can interchange glucose and mannose. What typically happens is there is an enzyme that first oxidizes the C2 group to a ketone, and then will reduce it with NADH, but deliver the hydride from the top face to make it glucose instead of mannose. Does that make sense? We could draw it out. We don't necessarily need to, but that's sort of how biology interchanges or epimerizes sugars. It'll oxidize the carbon where the stereochemistry needs to change, and then it's going to reduce it with a hydride from the right face to get us the right stereochemistry. So that's beta D manopyranose. You should be able to draw alpha D manopyranose as well. That would simply be the C1 epimer of beta D manopyranose, that is where the OH was down. And then the other one I want you to know that's biologically important is the C4 epimer. This is found a lot in, and this one is called beta D galactopyranose. And I'm running out of space to write that. Beta D galactopyranose. Again, everything's going to be the same as glucose, only at C4, the OH is going to be up axial instead of down equatorial. Okay, and in its open chain form, this is called D-galactose. The galacto part, that's going to sound like galaxy, and that's on purpose. Galaxy comes from the Greek word for milk because of the Milky Way. Galactose is found as a component of the disaccharide lactose, which is in milk. So if you've heard that word before, that's where galactose sort of comes from. And I'll show you the structure of lactose a little bit later. You should be able to draw the alpha D galactopyranose as well. Now, there is a C3 epimer of glucose. It does have a name. It is less biologically relevant, but just for completeness, we're going to draw it here. The C3 epimer of glucose is going to have the OH group down axial on carbon 3. And this one would be called beta D allopyranose. And in its open chain form, the correct name is D-allose. And then you should be able to also draw alpha D allopyranose. So glucose is where C2, C3, C4 are equatorial when you draw it like this. Mannose is where C2 is up instead of down. Allose is where C3 is down instead of up. And galactose is where C4 is up instead of down. So those are the ones that I want you to know. And be sure when you're looking at a carbohydrate, I know that I've told you it's important to focus in on the parts of the molecule that are changing, that are important in a reaction. But when you're dealing with a carbohydrate, it's also important to know which carbohydrate it is. So pay attention to the OH groups on C2, C3, and C4, and make sure nothing's changing there. We haven't done any reactions so far where stereochemistry is changing on those carbons, and we won't. And so just pay attention to that in reaction mechanisms. All right, the last thing I want to show you is the question of making acetals with carbohydrates, and those are called, in the context of carbohydrates, they are called glycosides. So a glycoside is a sugar acetal. So supposing you took a mixture of alpha and beta anomers of glucose. Sometimes organic chemists get lazy, often, and when we want to draw a mixture of alpha and beta anomers of D-glucopyranose, rather than draw the two different structures, we will draw a squiggly line here halfway between equatorial and axial, and that communicates that we've got both configurations there. Okay? You are free to do that too, by the way, when you mean a mixture of alpha and beta anomers. Now suppose I add methanol and I add a catalytic amount of acid. Suppose I use toluene sulfonic acid. You should predict what's going to happen next, remembering that glucose is a hemiacetal, and remembering that if I supply an excess of this alcohol, I should be able to make an acetal with one molecule of alcohol and the other molecule of glucose. All right, we'll pick that up on Monday. With that, have a good weekend.